Okay, so I guess I'll just jump right into it. I think there's like there's gonna be a few less people in today's session because I have some students that are like in Kuwait and Saudi Arabia and stuff like that, and I don't know if that was anybody's partners or what, but for them I have a special situation arranged, so they're not gonna actually be here because it's like 8 a.m. for them or whatever. So there's a little less people here today, but anyway, I guess I'm gonna jump right into it. Um, what we're doing today is essentially it's equations of motion, but really we're just going to be looking at one particular type of motion. We're also going to look at it in one dimension. But what we actually have here is a cart on a track. I don't know if you've looked at the lab yet, but it should be available for you to check out. We have a cart on a track, and it's going to roll down the track. And obviously, you're not going to be able to do any of this, but it happened, and just trust us, and we have some values for you. Now, I just want to mention how you break apart the forces acting on an object sliding down an inclined plane or the track, because that's going to be like probably the most useful for you. You'll probably be doing something like this soon in your actual class. And then I'm going to go into a little bit of calculus on kind of like when we talk about the plots like of position versus time, velocity versus time, acceleration versus time, and then we derive those expressions using just some basic integration. And then I'll let you go. The last time I did this lecture, it took about 20 minutes, 25 minutes tops or something. So we'll just get cracking. Essentially what we have in this lab is an inclined plane with an object flowing down it. So I'm going to go ahead and just kind of exaggerate the angle of this plane. Like so. There's an angle of elevation of this plane, put right there, call it theta. And we have some object. I'm just going to draw a box, but we have a cart, let's just say. And it's near frictionless, so we're going to ignore friction on this thing, but I'm not even worried about what that friction might be at this point. The thing is, whenever you're setting the force diagrams up for this situation, first of all, I'm going to declare, like in the actual lab, I'm going to say that this is the x direction and the y direction is like up and down off the plane, which means we're only going to have to deal with the x direction because this cart isn't going to come up off the plane. So anyway, so if we're looking at, that's the rotated reference frame that we're going to use for the lab, but that's kind of not part of this discussion here anyway. Right here, we can draw the one force vector we know is acting on this cart, which is gravity, and that's going to be straight down towards the center of the Earth. Okay, I'll call it Fg, force of gravity. The thing is that we can actually decompose that vector into two vectors that would then add to make that vector. We can decompose them into the x and y direction that I have set up in this little box over here, this little dotted box, whatever you want to call it, my little rotated reference frame. So I can say, well, there's going to be some force going this way, and there's going to be some force coming straight down. That's going to be the force that the block in the inclined plane feel between their surfaces, and then this force going down to the right towards the positive x direction is going to be the one that accelerates the block or the cart down the actual track. Now, what I can do is I can actually see this force of gravity and this normal force, which is what this is going to be here. Well, the normal force would really be the opposite to that, but that's going to be equivalent to magnitude. And this force here, which is accelerating, this force accelerating it down the track, I'll call F sub A, this force of acceleration. I can draw that F sub A vector down here at the bottom and kind of make it look like a right triangle, and then we can kind of do some stuff that we did last class. Here, though, where's my angle? Turns out if you draw this triangle just right, where you make the vertex of the triangle right there on the actual track, not in the middle of the block, just assuming that this block is like infinitely tiny, or it's like a point. What you can do is you can find that the angle here at the bottom of this triangle, this next to FG, between FG and FA, that's theta. It's the same theta as the angle of elevation of the track itself. Okay, so I have a right triangle right there, and skipping through some of the trig stuff, I can just set up an expression for F sub A, which is going to be Fg cosine theta. So that Fg, by the way, is going to be mg, mass times acceleration due to gravity, cosine theta. That just comes from Newton's second law, F equals ma, but for the force of gravity, A is actually the 9.81 meters per second squared, so I'm going to put a G there instead. So F equals mg. Let's call it Fg is equal to mg. So you can see that cosine theta is going to be some fraction, and that's going to make the Fg smaller by some fractional multiplier, and that is it's reasonable because what we have here is some force that's going to be less than the force due to gravity. It's not going to accelerate at 9.8 meters per second squared because it's at this angle, so it's going to accelerate at something less than that, and that's what this force will give us. So it'll give us the force, and then we can divide by mass to get acceleration if we want. The acceleration down the track, which I can call like a sub t or something, would then be g cosine theta. And that's me dividing the mass out of the situation. Because F over m is a, you divide the mass out of the right side, just get g cosine theta. Anyway, so that's kind of what we're doing here. Now, you don't really need to know that to do this lab, but that's just something I wanted to kind of give you some context, and this will help you solve these kinds of problems in the future anyway. Breaking down the forces acting on an angle on this inclined plane is a little weird because you got to remember where those angles are, but there you go. Also, it's kind of strange. You expect the force pulling you down the track to be an F, so you expect it to be an mg sine theta, just because that's the way it's intuitive to expect it like that, but it's reversed. It turns out your normal force is a sine, and your force down in the x direction is the cosine, which, anyway. So now what we're going to do is we're going to analyze the motion of this object. So this thing slides down the track, and we want to take a look at the position versus time, velocity versus time, and acceleration versus time really quickly. So this is going to be the position versus time plot. Time down here, x direction up here. X direction is just my position since I'm only doing one dimension here. Like I said, rotated reference frame. Now, if I try to look at what this data is going to look like, you're going to see something like if you actually ran this in the class, you would see your position at your different time values line up like so. You'd have your data kind of fluctuating around this point, but increasing, looking like that. And you're going to match some kind of line to this. And you're going to realize that this thing looks kind of parabolic. Okay, which is reasonable because it's, if you think about the kinematics expression we talked about last time, change of position is equal to initial velocity times time plus 1/2 at squared, and that looks exactly like your general quadratic standard form, which is ax squared plus bx plus c equals 0, or however you want to say it. But that's that form of ax squared plus bx plus c, okay, which is a parabolic form. So we kind of expect that. Now what's happening here is that your position is increasing, and the rate at which your position is increasing over time because it's accelerating down the track, right? Which means its velocity is continually increasing. Something I want to remind everybody of is the slope of this plot is rise over run, right? Let me get that look more like an equal sign. It's going to be rise over run. Rise just means rising up and down on the graph, which means changing your x value. So I'm going to say delta x, change in x. Over running along the graphs horizontally, that's going to be change in time. So you can see your slope is going to have units of change in position over change in time, which is going to be in meters per second, which is going to be your velocity. So your instantaneous slope at any point along this curve is the velocity at that time, okay? Which means if I wanted to plot my velocity, it'd be nice if I did this on the same page so you can kind of see it line up, but it's fine. Velocity on the vertical axis, time on the second axis here. Turns out, if you look at the slope of this thing along the entire path, you'll see that the slope is increasing linearly with time. And what you would just do is take several different slope values along this curve and just plot them on this next graph here. And what you're going to get is something that looks very linear, okay? Which makes sense. This is going to kind of look like the expression, your velocity is equal to your initial velocity plus acceleration times time, okay? That's a linear form right there, y equals mx plus b. This is what we talked about last class with the velocity formula. I believe we talked about this one. But there's also one you'll see in kinematics all the time in physics. Okay. So here I want to make one more, we'll put one more thing out here. This is linear, of course. Yeah, linear. Write that down. The other thing I want to point out is the slope here. Again, rise over run. But rising here is changing your velocity. That's going up and down on this plot means you're changing your velocity because that's the vertical axis. And the horizontal axis is time. So that's change of velocity over change in time. And you can kind of see where this is going. This is going to be meters per second over seconds, which is meters per second squared, which is my acceleration. Okay, so my slope of my velocity versus time graph is acceleration. Right? Slope equals acceleration. Now, one thing you can notice about this plot, about the acceleration in particular, is that, well, first of all, the slope of this velocity versus time graph is constant, right? It's just that upward angle constant the entire time because it's a line. So if I wanted to plot the acceleration, it's going to be whatever that slope is the entire time, so it's going to be a horizontal line. And this is a relationship you'll see all the time in physics. Your position looking like a parabola, position versus time, velocity versus time linear, then acceleration versus time constant. Now that's if your acceleration is constant. Of course, you're going to get different value. You're going to get totally different graphs if your acceleration is non-constant. Now in our case, gravity is the thing that's affecting this cart. It's being accelerated down the track due to gravity, and gravity is constant, right? So we're going to have a constant acceleration on this object. We're going to have a constant force applied. So let's do the derivation. Well, actually, before I do the derivation really quick, I wanted to point out a little calculus way to look at this, right? Here I was talking about the slopes, okay, rise over run, blah, 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 going back to, you know, maybe some like remedial stuff somewhat with rise over run. But the thing you want to notice here is that the slope of this graph is equal to this graph. That really means that the instantaneous rate of change of this position versus time plot at any point is the velocity, the instantaneous rate of change. And instantaneous rate of change is your derivative, right? So what this little exercise here is telling us is that you have some x of t, right? Turns out that dx dt is your velocity with respect to time, and dv dt is your acceleration with respect to time. Okay, that is, take the time derivative of your position and you'll get your velocity. So if you have some function for your position, take the time derivative, you get your velocity. If you have some function for your velocity, take the time derivative and you'll get your acceleration. Okay, or if you want to go backwards, you can do the antiderivative to get back to your position, which is how we're going to do the derivation now. So in that example, we have a block experiencing a constant force, right? Force is constant, and it's equal to mass times some acceleration. Okay, well, if F is constant, mass is constant too, so this F constant over mass is equal to my acceleration. Therefore, my acceleration is some constant. Okay, so I'm going to say that my function, my acceleration function with respect to time, my a of t for this example, just some block with experiencing a constant force. I don't say, it doesn't really matter what it's experiencing the force due to, it's just experiencing it. My a of t will be equal to some constant. I'll just call it a. Okay, so just some constant a. There it is. That's my acceleration. Now, because we know that dv dt is equal to a of t, that a of t is equal to a, basically we know that dv dt is equal to a, right? And then we can do like a separation of variables here, essentially. We're really just taking an integral both sides, but we can do separation of variables and we can turn this into dv equals a dt, and then do an integration on both sides. Okay, integrate both sides, integrate the left side, just integral dv. I'm just going to call that v of t. I'm making this indefinite integrals, by the way. I could say 0 to t or something, but I'm not going to do that. And then the other side, if I integrate with respect to t, I get at, right? And then plus some constant. I'm going to call this constant, let's see, I'm going to call it v naught. Why would I pick v naught? That's a weird constant to pick. You'll see. Okay, so just like you're doing your antiderivative, you're doing your integration and you don't have an actual limit, then you don't have like initial conditions, you have to add the constant to the end. That's what I did here. That's why I added the constant to the end. Okay, now I can see I have some expression here that we kind of recognize, don't we? That's my velocity with respect to time. It's v naught plus at, or at plus v naught, whatever. My acceleration times time plus my initial velocity. Okay, cool. But now I know that's what my Vt is, and I know that dx dt is equal to V of t, which is equal to V naught plus AT. I switch them around, fancy. Well, I can go ahead and do the same kind of thing. I can say, well, that means that dx, the integral of dx, is equal to the integral of V naught plus AT dt. All right. Again, I can integrate both sides, and on the left side, I'm going to get just x of t. So my position at some time value, some function of position here, or a function of time. On the right side, I will get, let's see, I'll get V naught t, right? And I'll get plus 1/2 AT squared, doing my anti-integration here, or my antiderivative, plus a constant, right? So I'll get something like plus, I'll call this one x naught for maybe an obvious reason. I'll go ahead and reorder this so you recognize it a little more. But that's x naught plus V naught t plus 1/2 AT squared. That is my position function. That's like the most used kinematics expression for your change in position, or your final position would be the left hand side. There usually what you see is x sub f, but here it's a position as a function of time. So it's x of t. Okay, well, those are the expressions that we're going to be proving for this lab. Essentially, the idea is we have derived these expressions, these equations of motions, one's for acceleration, one's for time, or one's for velocity, one's for position. And we're going to test how accurate those things are by putting a cart on a track and having it slide down the track, and the cart actually sends data back to the computer, which is its position, like how much distance it's traveled, and how much time has elapsed. And then from that information, we can go ahead and get the velocity versus time and the acceleration versus time as well. And that's what we're going to do. So without any further ado, I guess I'll go ahead and just walk us through the lab and what I'm, just to translate everything it says and tell you what I expect. And then I'll set us loose. Okay. So, let's see. Okay. So here's a lab. Here's a little intro, kind of like what we did. Talked about averages, which I'm not too worried about at this point. Same kind of deals before, right? You all put your names at the top, whoever's in the lab group. If one of your lab partners is absent, don't put their name in there. I had somebody ask me that question yesterday. Anyway, so okay, here's like kind of essentially what we did. Procedure, basically, don't worry about this. Is just telling you how to use the machine and plot the data and then try to fit a curve to it, which is something you don't get to do anyway, unfortunately. Which is probably the biggest skill here. Oh, looks like somebody fixed the typo. That's good. Okay, so here's your first graph. You can see this one kind of looks like the one I drew. It looks like the parabola one I drew, the position versus time. And it is. Here, this expression, you see x of t is equal to 0.8515 t squared. That right there is my position function. And you know what it's supposed to look like, right? It's supposed to be x of t equals x naught plus v naught t plus 1/2 at squared, okay? Well, there's no expression with a t, right? There's nothing with a t in front of it or next to it, so that means my initial velocity must be 0, right? There's no constant just floating in there by itself. That would be my x naught, right? If it's not there, it must be there, but just be a 0, so my initial position must also be 0, okay? I'm going to leave it to you to figure out what this 0.8515 is. That's the thing in front of the t squared, and you know it's supposed to be in front of the t squared, right? So what's my acceleration? Is it just 0.8518 or 8515, or is it? I don't know. You can check that out. Next plot here. That's literally it, right? You're just reading information off of this plot, off of this expression right here, knowing what it's supposed to look like, knowing what it does look like, and just inputting the values down here. Same kind of deal here. So this is your linear velocity plot. You can see they actually fit some curve to it, and the line that they were able to fit was v of t equals 1.703 t. This kind of looks like y equals mx plus b, right? It's like linear, but there's no y-intercept. There's no b value. But let's think about this in v. Let's think about it in terms of the equation of motion. This is like, actually, I think I can draw on this screen, can't I? I can. This looks like v equals v naught plus at, doesn't it? This one right here. Except there's no v naught value, is there? So I wonder what that means that the initial velocity value actually is, right? Okay, shocker. What's in front of the actual t is an a, right? A goes in front of the t, and there's a number in front of the t. I wonder if that means that's the, Okay. So without risk of making it too obvious, there you go. Okay. So next page here. That was pretty much that's pretty much the whole thing. Now it's just answering some questions. That's literally it, and that's gonna be a pretty short lab. Okay, using this expression, which is the one that we've basically been talking about, the master of all kinematics expressions, that guy right there. We're just gonna write down that equation and use the coefficients that we recorded in the other tables. That means we found out what V naught was, we found out what Y naught was, and we found out what A was, right? So just write it as an expression. So if you know that Y naught is 0, just write Y of t equals 0 plus, if you know what V naught is 0, then maybe like write 0 times t plus, and then if you know what A is, put 1/2 times whatever that A value is, and then t squared. Just write it out. That's literally all they want. That's fine. Again, same deal right here. It's the same exact as question 1, but just filling in this expression instead of the other one. Write down what A of t is. Okay. Kind of already told you, A of t is a constant, right? So what should go there is probably just a constant, right? A of t is your function, A is a function of time, but if there's no time value in that function, then it's going to be constant throughout time, and it's fine. We can still write A of t equals a constant. That's not wrong. Compare the answers found from questions 2 and 3. Write down a general statement that relates to velocity and position curves. What is a mathematical operation that relates the position and velocity curves? Well, earlier I was saying that the slope of your position curve is your velocity. I was saying the instantaneous rate of change of your position is your velocity, which basically says that the derivative of your position is your velocity, right? That's kind of what I want you to say here. That's pretty much just, I want you to explain that. Difference between speed and velocity. We talked about that a couple times, right? Scalar and vector. Let's you figure out which one is which. What happens to the speed and position function when the acceleration is constant? Well, that's the situation we're in, right? Our acceleration was constant. So what happened to the speed and position functions? They really should say velocity, I think, but what happened to your velocity function? What happened to your position function? Visually, right? It's kind of weird. It's like, they really want to know, like, I think they're really looking for, like, what does it look like? What it looks like. Okay. Kind of a weird question to ask. That's why I go through these labs with you, so that you know, because this question here is like, is that really all they're asking? Yeah, that's all I'm looking for. If you were to model through a position versus time graph the act of walking forward, what would happen to the slope if you were to walk faster? So if you accelerate, if you increase your speed of walking, what happens to your slope of your position curve? We talked about that in the notes. I'll let you figure that one out. Okay, what was the thing generating this constant force? Well, that one should be kind of obvious. It's gravity, right? You don't have to actually calculate mg cosine theta or anything like that. I'm just like, what is the thing that's causing this? Well, it's gravity. Is it possible to get a negative position? I'll accept either answer. Just give me a reason why. It's kind of silly. It's like, if you set up your, well, you know what? I'll just let you think about this one, and then you can answer me. I guess if it's set up the way it is, well, whatever. There we go. That's what I was going to say. So that's about it. Now I'm going to go ahead and put everybody in their groups. It looks like there might be a few less people today, though. So because of that, what I was saying, some people are going to have like a different arrangement with them. So I'm going to try to do the same groups I did last time, but there might be some people getting left out or whatever, and I'll just assign you randomly, or if I forgot where you're supposed to go, just let me know, okay? All right.